So I'll give you a minute or so, and then we'll get started. Okay, so the plan today is to finally get to the actual pulse sequence that is the most commonly run pulse sequence at the MRI center, and it's called multiband, which is it's a little slightly unclear, but it's also called SMS. And SMS stands for Simultaneous Multi-Slice. And so what we want to do is go over Simultaneous Multi-Slice. What is that? What does that mean? And it's kind of a hard one to understand. It involves kind of a version of grappa, and so I'll quickly go over how this grappa undersampling works. But let's first start off with just the actual pulse sequence. And the pulse sequence itself is kind of not very difficult to understand. So if we look at and it looks pretty much like a regular EPI scan, which is what we went over last time. And so the EPI scan was, you just do one RF pulse, and then you try to record all of the data for a slice just from a single RF pulse. So here's our RF pulse, and here's the slice select gradient. So we turn that on during the RF pulse. So if it was a regular, so here I'll put somebody in the actual position that they're in. So here's their brain in the magnet with their eyes looking up. So if we turn on that Z gradient, so that's the GZ, and here's the RF in. If we turn on the GZ gradient, that's going to, so here's the bore like that. So what is the GZ gradient? It's a gradient that changes as you go in the Z direction. So this is the direction of the bore, so it's a gradient like that. And the strength of the Z component, so it's a change in the strength of the Z component as you move in the Z direction. That's the Z gradient. And so what's going to happen if you do one RF pulse is that there'll be some part of the brain, like say about here, that just happens to be at the right part of the, whatever the part of the Z gradient that corresponds to the frequency band of your RF pulse. And so what you'll do is you'll excite that slice. That's just the basic sort of mechanism of how we excite a slice. So you put a gradient on, and then you play out a narrow band of frequencies, and that just synchronizes the proton precession just in that one slice. So what is multiband? Well, we just add another sync pulse on top of that. So this guy is, frequency 1, and this is frequency 2. So we can just calculate another sync pulse that makes a different band of frequencies and just tack that on top. And how can that work? Well, the Fourier transform is all linear, and so that's all good. So you can just add things on top of each other, and so you can just pile some sync pulses. One problem that comes up is that you could have a problem with too much RF power, because like the very center of the sync is a high peak in RF power, and so there's various tricky ways of maybe trying to offset them a little bit so that all the peaks don't come exactly at the same time. and fix up the phase problems you get from that. But in any case, you can basically just add two sync pulses to each other. And so if you do that, what's going to happen? Well, there'll be another band, another slice activated at the same time. So you'll get actually a second slice. So this, say this is, from, frequency 1, and this guy's from frequency 2. So you just have one gradient on, the Z gradient, and then you have one, that's one slice select gradient, but we get two slices. And then how do we record the slices? We just record them. I didn't put in the fat sat, so let's just put, fat. We have to do, you have to sort of like get rid of the fat saturation. We talked about that last time. You do that, but I didn't put it in there. Okay, so then we need to record, and so we go to the left side of the left lower corner of K-space, and then just do what we did last time, which was, to do this back and forth across K-space business. And so you have these big gradients that make the beep that are going back and forth. And, et cetera, until we record the center of K-space and then continue, And so that's going to make a whole series of echoes. This first one is very small because we were all the way down in the corner of K-space. And then, when we get to the center of K-space, it's going to be bigger, and that will be our effective echo time. So there's our big echo. This is, TE effective, center of K-space. And all these will have echoes. And then, in addition, we have the little blips, and the little blips come right as you get ready to record another line of K-space to sort of move you up in K-space. So that part's exactly the same as before for our EPI. But the only difference is we add some blips here. So let's add a couple blips there. Let's do some up and down blips. We'll explain. So that's basically the only pulse sequence difference between a regular EPI and a multiband EPI. We just added another RF pulse, a second band of frequencies piled on top of the first band with the gradient on. That selects multiple slices. And then we got these blips, which we haven't explained, these second set of blips. And so this was originally called caipirinha, after the Brazilian drink. And then it was called blipped caipirinha. And then they said, well, that's kind of a little bit of a mouthful, so now it's called multiband or simultaneous multi-slice. Simultaneous multi-slice. So now what? What do these blips do? So this is a little counterintuitive. So if we did no blips, so say we did no blips, so this is no GZ blips, then what would happen is you would end up with one slice. Say this is the temporal lobe, so you're going through the temporal lobes like that. And then you'd end up with another slice on top of it. So then there will be another slice, like from higher up in the brain, like that. It was just layered on top of it. And there's various ways to undo that, but what the advantage of adding these extra blips here is we can cause these slices to be less overlapped. Now, that's a little confusing. So let's say this is, this is our our x direction here, and this is the y direction. So these are our z blips. So these are, extra g z blips. And this part is regular EPI. So we've got these extra z blips, and so why do the z blips cause a shift in the y direction? So let's just say what happens. So what happens is if you put this z blip on, what will happen is it will have the effect of essentially shifting these two images so that they're not overlapped as much. They'll still be overlapped some, typically, but they won't be overlapped as much. So why do they get, so this is GZ blips on. So what have we done? So we've essentially added some phase, because remember, all the gradients affect the same thing. They just mess with the phase of the precession. They're all sort of, the only reason they seem to not interact with each other is because they're at right angles to each other. But they're all affecting the same thing. And so if we advance the phase with the z gradient while we're doing all this other messing around, it's going to add a pedestal of phase. So what's going on here? So it basically, add a pedestal of phase, to everything in slice, to everything in both slices, right? In both slices. But it's going to be different in the two slices. So, different in two slices. And why is that? Because you're in a different part of so here's the z gradient. So this is a GZ gradient, just like this one, like our slice select one. So it's going to be, if we turn that blip on, the blip is going to look the same way. And so it's going to add a different amount of phase to this slice and that slice. So say this slice happened to be in the middle of the gradient. Say this was like the, for example, GC at this position equals 0. So say we're just in the middle of the gradient, so we haven't sort of like added or subtracted anything from the B0. And then this one has subtracted some from B0. So what that's going to do is that would just move one of the slices. But the last trick is why. So why does it do that? So there's two things, and the reason it does that is because we'll go over this in more detail next week, the Fourier shift theorem, but we already kind of did this. We already did this intuitively. We said that if you just mess with the phase in k-space, because all our data is coming in k-space, if you advance the phase of everybody in k-space, all the different spatial frequencies, just tweak the magnetization vector, precession magnetization vector of everybody, so that precession, the magnetization is varying and twisting around as you go across real space. If we just essentially add, say, 45 degrees to everybody, and all different spatial frequencies also, so add 45 degrees to the entire set for spatial frequency 2, add 45 degrees to the entire set for spatial frequency 3, do all of them. And the blip does that because it happens before you record any of the data, so it just advances everybody by 45 degrees, and then record the data. What does that do? That just causes a shift when you do the inverse Fourier transform. So a phase difference causes a spatial shift. So that's basically, phase diff causes, spatial shift. That's the Fourier shift theorem. Okay, but now, last but not least, why did it only happen in the y direction? It didn't happen in the x direction. And, the x direction's phase encoding too. And so why does it only happen in the y direction? So the reason it only happens in the y direction is because when in the x direction, we've got these humongous gradients going back and forth and muscling stuff around. In the y direction, we got these tiny little blips. And so the tiny little blips are much smaller relative to these gigantic ones. And so the end result is if you mess something up with the phase, it's going to affect the y direction a lot more. Now, to fully understand this, that's like 2 weeks from now. We haven't sort of come to that. But the end result is that you basically just shift stuff in the phasing code direction. So this is, slice, phase, readout. Okay, so that's all good. So we've helped ourselves. We've kind of unoverlapped the slices by putting those extra blips in there. So we turn on a z gradient, and that causes the image to shift in the y direction. But now you can see we're slowly but surely messing things up. And so we'll say several tricks for sort of fixing this. So the first trick is, so the question is, how the blip can work, how z blip can work. So our first idea is, say, and especially like just flipping it back and forth. So why do we want to flip it back and forth? So the problem is if we kept doing it in the same direction, what would happen is we would slowly build up stripes in the z direction and kill our signal. And so if we did 128 of those all in the same direction, you'd eventually end up with 128 stripes in the z direction, and that would just wipe out your signal. So we have to go back and forth. But the problem is when you go back and forth, that doesn't completely compute. But let's just say this slice happens to be at the 0 of the gradient, okay? So that guy, when you turn the blip on, if it happens be right at the 0, it won't do anything to it. It won't add any phase to it. And then we can say have an 180 degree phase flip at this part of the gradient, right here. And that's convenient because if we do a negative 180 degree flip, then that's exactly the same as a positive 180 degree flip. And so it doesn't matter if we go up or down. So that's trick number one. So it's very specific. It only works for the center of the gradient on the slice that's off there. So, but you can see that you can blip up and down and not mess things up and get the same result for blip up and down for a slice that's offset, and then get no effect on the slice that's in the center. So that doesn't seem very general, and so trick number two, what we could do is essentially add phase. So say this 0 isn't actually 0, and you've got a slice that's at 45. It's getting a 45 phase advance. Obviously, if we do minus 45, we're not going to get the same thing. We're not going to get the same effect. It's going to be a different signal. So basically, we just sort of add phase before reconstruct. For slices not at 0 and 180. Okay, so that's just, so what we do is we do the blips up and down. They cause, all hell to break loose in the case-based data, and then afterwards we just go in and say, like, well, we know that guy was 45, so I'll subtract 45 off of him and make it back to 0. So that's kind of like the trick too for allowing you to do slices. But then what about 3 slices? What if you wanted to excite 3 slices? And so trick number 3 is you do something that looks like a couple, or say you want to do 4 slices at the same time, you do something that looks like that. So you do like 3 up blips and then a bigger down blip, and then patch the phases. So then patch the phases. Phases, phase of k-space before reconstruct. So now you can see there's all different kinds of tricky ways of before recon. Okay, so that's the pulse sequence. So the actual pulse sequence, will have like a bunch of up, like 3 up or 4 up, and then 1 bigger down. And that will solve the problem of not killing our signal because we're wrapping up spin stripes in the z direction. But we still haven't said how do we sort of actually on-overlap the slices, because we still have to on-overlap the slices, because especially here you got 2 that are almost on-overlap, but you can accelerate by a factor of 8. And so in that case, you'll have you'll have this mess of slices all on top of each other like this. So how on earth could you sort of on-overlap 8 slices, which you actually can? So to do this, we have to go back to grappa, and so let's just go. I just went over it, but I'll go over it again, just to make it stick. So the grappa idea was we try to interpolate the data in k-space. Don't collect all of k-space. Leave some out. And if you do that, which you'll see in the homework, what happens is you'll have your field of view, and you'll cause overlap, or cause wraparound. And so notice what we're seeing here looks like wraparound. So that's kind of a hint as to where we're going. So the regular grappa, the idea of regular grappa is first you do a pre-scan collecting all this is before the main scan, collect all k-space, all lines. So what does that look like? We just have our k-space data here, and we collect all the lines of k. Don't leave any out. And mainly we'll sort of concentrate on the middle of k-space because that's where the signal is the biggest. And what was the theory for why we could possibly leave out k-space lines? Because remember, in our basic Fourier transform, every spatial frequency is orthogonal equals uncorrelated to every other spatial frequency. And so if we leave out a spatial frequency, we can't easily predict it from the other spatial frequencies because it's a completely uncorrelated signal, an orthogonal signal, uncorrelated signal. But if we have a coil that has a hotspot in it, if we have a coil that has a hotspot in it, that essentially corresponds to, that causes a single spatial frequency in k-space to be smeared to the surrounding spatial frequencies. That sort of like variation in brightness across the coil. And that argument applies to all spatial frequencies. So the amount of blurring of each spatial frequency caused by a coil that has a hotspot in it, like a sort of like a Gaussian, like, fall off, will cause every single spatial frequency in k-space to be equally blurred. And so that's why we essentially sort of just try to calculate the blur just with the center of k-space where the signal is really good. And so then what we do, and then you do the same thing for, there's multiple coils. So there's a second coil here. So here's coil 2. Here's coil 1. Because we've got these local coils that don't pick up from the whole brain. So do the same thing for coil 2. Collect all the data in a pre-scan. And then when we actually collect the actual data, we leave every other line out. So, or every 2 out of 3 lines, or 4 out of 3 lines out. And so we'll just do it for 2. So we collect the data, and then leave this guy out, and then collect the data, and leave this guy out. And if we just reconstructed that thing without doing anything else, we will have halved our field of view. And why is that? Well, we essentially undersampled the spatial frequencies. If you remember back to the k-space, like if you don't sample the spatial frequencies closely enough, what it causes is it causes the replicas to come in. And so this is going to have your field of view and so if you just reconstructed it directly instead of the brain hoping for what you would get, what's going to happen is you'll have another copy of the brain here on top of the front and another copy of the brain here on top of the back. And so what it will do is it will effectively halve your field of view. So, this distance will be just half of what it used to be before if we leave out every other line. So that's not good. That's not going to make a nice picture. And so, but taking advantage of the fact that the information for each spatial frequency in k-space has been smeared because of the coil having this slow fall-off function across real space, what we can do is we can take this data where we collected all the data and then take a point here and try to predict it from the surrounding points. So we actually have the data here, and so what we can do is we can train a little predictor to say, given these points, predict what the actual data that we recorded was at that point. And so once we have that little machine that says that's how we predict that one, because we actually know what it was, because we collected it, do the same thing over here. So here, now you've got 3 data points over 6 data points over here, and we can use them to predict what that data point is. And in fact, you can do this for multiple coils, so you're actually using sort of data from multiple coils to predict. So there's, multiple coils go into this. Yeah, multiple coils. Coils data goes into this. So that's how Grappa works. So it interpolates. You leave out data in k-space, and then it fills it in because some of this, each frequency has been smeared out to nearby spatial frequencies by having this local fall-off coil. And so then we collect all the data and then use all the data to sort of make a little filler inner that will allow us to fill in the data before we do our inverse Fourier transform. And so that works great. So you can collect half the data and still get an image that doesn't have any overlap in it. So how is this related to multiband? Well, it's almost like we left out some of the data, even though we didn't. So let's just look at, what happens normally. So what happens normally is we've got a brain, and when we do our data collection and leave out half the lines, and then do an inverse Fourier transform, we end up with what I just showed you there. So what happens is, here's the brain, but then it ends up with these replicas intruding from the surrounding guys, and so it ends up having your field of view. So your field of view, just gets half of what it is. So now let's look at what we did for the multiband. So in the multiband, it's kind of as if we, I'll draw a rectangular k-space, but that's not quite right. You should think of it as it's going up to the same kx. So this is, same ky. So here's ky, max ky, and that's the same here. So those guys are supposed to be equal. So the same max ky. I drew it as a rectangle just so that it doesn't get too crowded. Okay, so it almost looks like, sorry. Here's the max ky over here, max ky. So it almost looks like we had a real situation, which was, say, 3 slices. So we had like 3 slices like this. Okay, say this was the real world. It's obviously not the real world because there's only one brain in there, but so here's, say we had like a situation like that with 3 completely unoverlapped slices, and we collected data on it, but let's say and here's max ky, say those are the same, max ky, so these guys are the same, even though I drew it as a rectangle. Okay, so it's as if we left out some lines. So if we had left out, just recorded, 1 line and then left out 2 lines, and then recorded another line and then left out 2 lines. If we inverse Fourier transform this, what would we get? We would get some overlapping slices. So we would get what we actually see when we record a single multiband image. We would see, 1 slice here, and then there would be another slice on top of it, like here, and another slice on top of that, like say some temporal lobes. So we would see 3 slices on top. However, we actually recorded all the data. We didn't leave out any slices. So how can we fix this in a, so this is, so here's our original grappa. This guy is our original grappa. So this is a cool thing. So we just invent something called slice grappa. So slice grappa is kind of like original grappa, except that it actually. So we're going to have to collect some data, some full data somehow, in order to be able to generate this little fixer that fills in the missing data. But we've already collected all the lines of k-space for our overlapping image. We didn't actually leave it out. So this is, as if we left out lines. but we didn't. And so what can we do? We can collect data that doesn't have multiple slices turned on. And so the idea is collect data for all the slices in the brain, but don't turn on the multi-slice business. So here's so basically, pre-scan. So it's a scan before the main scan. So pre-scan, collect slices, without multi-slice. And so when you run one of these scans, what happens is, for about the first 10 seconds, we essentially collect data without the multi-slice turned on. And then what we can do is we can basically construct multiple case spaces using something that's sort of like grappa. And so what is the data we actually collected? Well, we actually collected every line of case space with the multi-slice stimulation turned on. So we actually did collect all of case space. So we didn't leave out any lines, but it's as if we left out some lines. It's as if we left out lines causing the replicas to come in. And so what do we do? Well, we take this data where we didn't leave out, we didn't turn on the multi-slice, and we use that data to generate a little fixer that will allow us to essentially generate 3 case spaces for each, one for each slice. And so these will be full case spaces that have all the lines in them. And then we can, but it's using a similar strategy to effectively sort of fill in these missing lines. So the idea is we fill in missing. They're not actually missing because we actually collected them all. But fill in missing lines using a grappa kernel. Grappa kernel fixer, made from non-multiband. Pre-scan. Okay, so that, and so now that we've sort of essentially generated 3 case spaces out of our 1 case space using our little filler inner, then we can just Fourier transform those guys and ft minus 1 and then get our separate slices. So then we can just get our full slices completely separated, even though they're, so that's ft minus 1. So this thing is used at that point to turn this is the, actual full case space with, multiband on. So that's the twisted way in which it, the way that multiband works. Now, when you first think of this, like if you kind of read in the literature, you'll see something like this. How does multiband work? Well, it's got these local coils, and it uses the local coils, the spatial information from the local coils, to take the slices apart. That's kind of like the way the way it's marketed. And in some sense, that sort of is true. It's actually using the local coils, which have the effect of smearing data in K-space to allow you to generate a little fixer that will fill in the missing data. But this doesn't really give you sort of a concrete way for how that spatial information from each coil could actually be used. And this is how it's actually done. So you excite multi-slices. You try to separate them a little bit with the Z blips, but they're still way overlapping. And then what you do is you take that one set of K-space data that you collected. Well, there's a version of this for every coil. Remember, this is for each coil. So you take that data for each coil, and then you fill it in by doing this thing that's sort of like grappa, but it's not quite like it, but it's the same procedure where you make a little fixer based on the full data, and then you use that fixer to fill in the missing lines of K-space, because you're tripling the lines of K-space here, and then you inverse Fourier transform it and get your on-overlap slices. So you can see why so basically virtually all functional MRI is done this way. And I would wager that 99.9% of the people who are doing it don't understand how it works. And why is it worthwhile understanding how it works? Well, it's worthwhile to get a feel for what the possible artifacts are. So if you haven't perfectly on-overlapped the slices, obviously you're going to cause data from one part of the brain to be pasted onto data from another part of the brain. And this could be particularly damaging if you're doing something like, say you're using functional MRI data to look at functional correlations between different parts of the brain. Does this part of the brain sort of go up? Does the orbital frontal cortex go up when I see something at the same time? Or does, if I'm preparing to make a movement, do several disparate parts of the brain start to go up? Obviously, if you haven't perfectly on-overlapped the slices, that could seriously mess up that kind of data, because it will actually take some activation from one part of the brain and paste it onto another part of the brain. And so I think it's important to understand sort of how this procedure works, even though 99.9% of the people that use it don't. And so you're going to be the part of the 0.1% that actually understands how this is done, and why it requires multiple coils. Okay, so any questions about multiband, the most commonly used functional MRI sequence currently? So in practical terms, not much to it. It just looks like a regular EPI scan, and you've got some extra blips, and you've got some extra RF pulses that pile on top of each other. Okay, so if you go to the readings page, you can see the original papers on this, and you can just try to sort of look at some more of the details. But this is hopefully enough of a introduction to it so that it won't be completely Greek when you try to go into the papers. Okay, so any multiband questions? Last multiband questions. Or grappa questions, sort of like how does this work? Sort of like filling in, making a little fixer that uses the surrounding points in K-space to interpolate and sort of fill in, based on actually K-space that is completely filled. One thing worth mentioning is that all these methods, they're collecting extra scans. So you're collecting scans at the beginning of grappa. Those scans are used to fill in every single data point that you later collect. And so one thing to worry about is, what if something screwed up, like the unruly 4-year-old in the scanner jerked his head around right during the collection of these, of these pre-scan where you collected the data without the multiband multiple slice on, well, then what's going to happen is, since that is used to generate every single other image in your later data set, all the 8 minutes of images afterwards, it's going to screw them up too. And so one of the problems with these kinds of methods, same with grappa, is if you move during the very start of the scan, it could potentially screw up the whole rest of the scan. And this is particularly important in a functional scan, because typically what happens when you're doing this pre-scan here, what happens is this task hasn't started yet, because you've got to do that 20, 30 seconds of data collection before the scan actually starts. And so the subject may have the feeling like, well, the scan hasn't started yet, and so I might move a little bit right here at the most critical part. So it's important, if you're scanning anybody, to tell them, do not move even before the task starts. Because I've been in the scanner numerous times, and I have the same feeling. I just, feel like, well, I don't have to fixate yet because the scan hasn't actually started, but actually it has. So that's another issue with these kinds of scans. You could end up with some bad data that contaminates the whole rest of the scan. So now, why do you want to do this? Why does everybody do this? Well, you get 4 times as many slices per second. So who wouldn't want to do that? You get 4 times as much data. Literally, it just quadrupled your data with almost no cost. So you can do more slices. You can do slices more rapidly. You can scan the brain every second or every half a second, instead of like 2 or 3 seconds to scan the whole brain. Or you can go and still take 2 or 3 seconds to scan the brain, but scan it at a higher resolution, because now you've got more slices, because if you take thinner slices, you're going to have to do more slices. So everybody does this. So it's worthwhile sort of going through it, how it actually works. Okay, so in the last -1 minute, no, there's actually 1 minute left to class, but in the last 3 minutes, I'll go over echo volume imaging. So this one is pretty much like regular EPI, but 3D. So this is 3D. And I always say, like, this is like fusion. It's the power source of the future, and it always will be. So they've been working on it for like about 60 years now, and it hasn't worked. It's probably not going to work. So when we look at regular structural scans, they're all 3D now. And why are they 3D? Because you get more, you're stimulating the whole brain at once, and so you just get more data. And so virtually every single structural sequence is 3D because of the extra signal. So why can't we do that with EPI? And it turns out you can do it with EPI. So what we would do is we would select a volume. So just select a whole volume here, like a slab, and then do our regular EPI. So, go to the corner of K-space. So this is, RF, GZ, GY, GX, RF out. And then just do our regular readout, where we just go back and forth across K-space. But the only difference is just do a bunch of phase encode steps over here. So what does that do? So that basically collects a cube of K-space instead of a slice. So what does that look like in K-space? So now here's our K-space, and so here's like KX, and here's say KZ, and here's ky. So we start at the middle. So here's, I'm trying to sort of like draw the middle of k-space. So here's the middle of k-space. And that's sort of, kz coming out at you. So there's the middle. So what we do is we do an RF pulse, and the RF pulse pops us to the middle, and then we turn on all three gradients, and that will move us from the middle to the corner of k-space like that. So that would be, point B. So that's point B. And then we go through k-space and collect a whole plane of k-space. Here's the blips. So we collect a whole plane of k-space. So we go like this, back and forth, etc. And collect a whole plane, not a slice. So it's not a slice because remember the data is coming from the entire head. So we collect a whole slice, and then when we're done, we just do another one, which is just like the previous one. It excites the same slab. So this is, same slab. And the only difference is that we're just doing a different Z phasing code. And then, everything else the same, etc., all same, except for this. And so we would just start off at this one, and then now we do a higher one. And so what does that look like here? Well, we go back to the center of k-space because we did another RF pulse. So this could be like our, less than 90 because we're doing these much quicker. Less than 90, both of these guys. And so we go back to the center of k-space, and then what we would do is we would come to like the next plane of k-space right here. So that's the next plane of k-space. Supposed to be up there, sorry. So that would then, put us in our next plane of k-space, and then we would collect that next plane over. So we haven't done any slice yet. We're just exciting the whole volume every time, and then collecting one plane, do a different phasing code on the G, Z, collect another plane, and then essentially collect this cube of k-space. So it would take, 1 to 2 seconds to collect cube. Now, in general, it's going to be much better than echoplanar because we've excited the whole brain every single time. So we're going to get a signal, instead of just getting a signal from a slice at a time, we're getting a signal from the entire brain. So it's like fusion. It's going to be better. It's going to be better. But why don't people use it? Well, the problem is that you could move in between, like, for instance, even something like the heartbeat. The heartbeat will sort of cause the brain to pulse a little bit. And so when we record the next slab of k-space, some movement will have occurred. And that's going to cause artifacts in the reconstruction and start to kill your signal to noise. And so one of the reasons that's prevented people from using this is that with regular EPI, the slice is collected just in an instant, like less than 1/10 of a second. And so movement isn't as much of an issue. I mean, you might ruin one image, but who cares? You've got 1,000 images to work with. And so because of that, it's easier to fix it afterwards. Here, what's going to happen is you only get all your images after 2 seconds to 1 or 2 or 3 seconds of data collection, and movement could have occurred definitely within there. And so that's the problem with it. But somebody will eventually make this work, and how they'll make it work is they'll do some additional scans to try to calculate what the movement was, and then feed that back into the system and undo the movement before you reconstruct the k-space. And the advantage of it is you just get a lot more signal, because every single data point in this 3D cube of k-space, so this is a 3D cube of k-space, comes from the entire head. And so that's going to be a big signal to noise advantage for, like, especially for recording something deep in the brain, like, you know, the basal ganglia or the thalamus or all these deeper parts of the brain that are farther away from the head coil, where the signal to noise goes down because it's far away from the head coil. Okay, so that's echo volume imaging. I mean, they named it that so that it looked like EPI. So it's, you know, echo planar imaging, echo volume imaging. And we have this on a scanner too, if you want to do that. So, like I said, it's the wave of the future. It always will be, probably. But no, somebody will eventually sort of figure out how to deal with the motion artifact in it. And it potentially could be like another doubling of your signal to noise. Okay, we reached the bitter end. Any questions about echo volume imaging or grappa or multiband? And people have tried, you know, what about, can we combine echo volume imaging with grappa? Can excite multiple slabs at the same time? So this one, I think this one has a bright future ahead of it. This will eventually maybe the next big thing, you know, a couple years from now. Okay, I think we'll end it there then.